All right, stoichiometry. Fun word to spell. Now, let's just have a look at this equation here. Now, this is a balanced equation, all right? We're looking at the first one. Okay, this is a balanced equation. What a balanced equation shows is that the number of atoms on the left-hand side and on the right-hand side are conserved, i.e. that they don't change in number. That ideally shows the law of conservation of mass. So the idea is that if there are, there's one S here and then two S's there, there's going to be three S's on the other side, right? That's what this whole idea of a balanced equation is. And so the idea would be that if I had, so I've got three S's on the left, three S's on the right, but if I had 300 S's on the left, I would have to have 300 S's on the right as well. All right? So the idea is that we have equal number of particles on both sides of any particular reaction. That means that gives us the ability to calculate how many particles of a particular reactant there is on one side of the equation and on the other side of the equation, using what we were working out before with the number of moles. So the idea would be something along the lines of this. This is actually not this is okay. All right. If I have one molecule, or one atom of this one because it's actually an atom, I would need 2 molecules of this to react with it. All right, one atom of that requires 2 molecules of that, which then produces 3 molecules of this and 2 molecules of this. Okay, so that would be that if we had those 1 atom and 2 molecules of the reactants, you would form 3 molecules and 2 molecules of the products, right? This can be extended to, further on. If, say, I had 10 atoms of this, how many molecules of H2SO4 would I need? How many? 20. I would need 20 of those. I would produce 30 of these, and I would make 20 of those. Happy with that idea that whatever works for an atom will work for 10 atoms. Will be the same for 100 atoms, right? It'll be the same for 1,000 atoms. The process is still the same, right? And then if we go even to larger numbers, to not atoms, but instead moles, okay? Remember, mole is just a really large number, right? 6.022 times 10 to the 23. That means how many moles of this one would I need, of the H2SO4 would I need? I would need 2 mole. How many mole of these two would I make? How many? How many moles of SO2? 3 mole. And how many moles of H2O? 2 mole. Happy with that idea? All right. Then we can even go a little bit further, and let's just do a little bit of, oh no, I have 1.4 moles here. Oh, decimal places now, sir. All right. How many moles of H2SO4 would I need to react with it? 2 times 1.4, which is? Quick math, 2.8. What would be the number of moles of SO2 produced? 3 times 1.4, which would be 4.2. And then this would be how much? 2.8. Happy with that? Now here's the thing. This is what you did that in your head, understanding ratios. But you can turn that into a formula, okay? The number of moles of your unknown substance is equal to the number of moles of your known substance times a specific ratio, right? A specific ratio. And that ratio is the coefficient, oh, I might zoom in a bit here. It's the coefficient of your unknown over the coefficient of your known. That's the ratio that you just applied in your head in that case, right? So let's give that a go in this example here. Okay, so let's say instead I have, nope, I don't want that. What am I doing? Why is it such a big eraser? No, stop it. Okay. What the hell? Why is it such a big thing? Anyway, come on, erase. No.
Pause the video to save embarrassment.
No, I don't have embarrassment when things go wrong. I just fix things. Okay, so let's just do this one instead. Let's do 3.2 mole of this one. Okay, 3.2 mole of this one here. Right, so now I'm going to apply this equation over here. This equation over here to work out the number of moles of all the others. So let's work out the number of moles of SO2. Right? What would I write? I would have to write out the number of moles of my known. My known is the one that I know the amount of, which is the 3.2. Oh, that's really actually not very clear on the TVs, is it? No matter. All right, 3.2 over here. Let me make it wider, a bit than a dot. Okay, 3.2. That's too fat. Okay, so 3.2, whoops, times. Now, what's the coefficient of my unknown? My unknown is the SO2, which is what I'm trying to work out over here. So it's 3 over how much? 2. Happy with that idea, but it's going to be 3 over 2 will get me the number of moles of that, right? 3 over 2 of 3.2 is some value. Sorry, what? 4.8. Yeah? Makes sense. Okay. Is it? I trust you.
I don't trust myself, sir.
Yeah, 4.8. Okay, cool. Right, what's the unit going to be? Mole. Okay, so this equation allows you to work out the number of moles of any of the other substances, either reactants or products, using the number of moles of one of them that you know. Okay? So let's have a look at this question and what this question is actually asking us to do. For each of the equations below, determine the moles of the product that would form if 0.25 mole of the first reactant were to fully react. Okay? So we're looking for the moles of the products if we have 0.25 moles of the first reactant. So let's go solve for this one here. I have 0.25 mole of that one. I need to work out what that one is there. So I could do the number of moles of SO2 would be equal to what? What would I write first? What would I write first, Cassidy?
Sorry, where are we?
We are working out if this one here, I have 0.25 moles of it. I need to work out how many moles of that I have.
Wouldn't it be the same?
It would be the same, but we have to show our working. So we got to show this here and that here.
It's just like 0.25 times like 1 over 1.
Not 1 over 1,
2 over 2.
2 over 2. Good. Show your working. All right? Which would be 0.25. That's nice and easy. All right? And again, it would be 0.25 for the water as well because it's a 2 over 2 ratio, but you could show your working. All right? One thing that I didn't go through yesterday is that you really need to be able to structure your answers in this way. What I'm doing is I'm showing what I'm solving and for what chemical I'm solving it for. I'm solving the number of moles for this whatever unknown. I'm solving for the number of moles of SO2 here. Okay? If you do know the number of moles, then you can go further and work out the mass of something. Who remembers the equation that we learned yesterday for working out the relationship between moles and mass? N is equal to mass over molar mass, or relative formula mass. All right? So, we could use that equation to work out the mass of SO2. Okay? So we would be like, okay, if I want to find out the mass of SO2, it would be the number of moles, 0.25, times whatever the molar mass of SO2 is, which happens to be 64 point something. All right? 64 and a bit. 0.6. Okay? And that would be the mass of the SO2 there. Okay? So, happy with that idea that this is the equation that you have to know. The number of moles of unknown is equal to the number of moles of known times the coefficient of the unknown over the coefficient of the known. You have to show that working when you do your working out, and then you can work out the mass from the moles later on. Okay? So what I wanted to do is just show you the way that you're going to think of these calculations. What you've got to recognize is that the number of moles of your known, this is the known side, can be solved for the number of moles of the unknown via stoichiometry. Okay? However, how we get the number of moles of our known might be very different. We might use the number of particles, which would be number of moles equals the number of particles over Avogadro's number. We don't use this one very often, but it could be. But you could also get number of moles from the mass. Number of moles is equal to, from the mass, little m over big M. All right? And then once you've gotten the number of moles of your known, you can work out via stoichiometry the number of moles of your unknown. And then you can work out the number of particles if you wanted to. Right? It'd be the number of particles is equal to the number of moles times Avogadro's number. Or you could work out the mass of something, because then you'd say, okay, well then the mass is equal to the number of moles times the molar mass. Right? And then if you're really clever, right, you could even work out the molar mass of something if you were given the mass and the number of moles. Okay? So the number of the molar mass you could be solved by doing big M is equal to what? M over N. But the idea is that we follow this along. Wherever we start with that one or that one. We move to here. Then we get to here via stoichiometry. And then we solve for that one, or that one. Okay? That's the process for these calculations so far, and that's where we'll be moving towards. All right? So